Please see the video description for a full list of disclaimers, including the ones here, plus a timeline and helpful resources and links. Please support the channel by using our affiliate links.
My name is Carl Dietrich. I'm a partner in SDRS Wireless and also a research faculty member at Virginia Tech. We've talked about some of the simulations in the hands-on learning for radio frequency spectrum innovation, or HLSI series. This is one among many simulations that we haven't yet discussed, and today we'll get into a little bit more detail about some of the graphics and the controls on the user interface for this simulation. And some of the other simulations have a similar user interface, so this description will apply to them as well. We saw an earlier simulation that used the information theoretic channel capacity of an additive white Gaussian noise channel to calculate an upper bound for a possible data rate achievable with a signal of a given bandwidth and signal-to-noise ratio. We'll keep that concept in mind today and use it some as well in a simulation of a signal in a fading channel. Now, signals can fade due to multipath or obstructions or other effects in a wireless channel. And without trying to mimic a particular fading distribution or function, we do show some fading in this example. In the user interface, you'll see some familiar elements. Here you'll see a slider, and in this case, rather than changing the frequency, the bandwidth, or the power level, all of which are fixed in this simulation, we'll be changing the modulation and coding scheme. And the idea there is that there are multiple possible digital modulations. Some send more bits per symbol, meaning they can send more bits at a time and achieve a higher data rate for a given signal bandwidth than would be achieved with lower order modulations. The simulation also accounts for the effects of forward error correction. Forward error correction encompasses several methods of adding redundancy to a bit stream so that the received bits can be corrected if any errors occur during transmission. This slider will allow us to select from among about 12 different combinations of modulation encoding, or modulation encoding schemes, abbreviated MCS. The left side represents schemes that are more robust yet slower. On the right side, we have some that are more aggressive, using those higher order modulations, and less powerful forward error correction, which allows those combinations to achieve higher bit rates at the expense of robustness. Basically, we want to use the schemes on the right when channel conditions are good, that is, when SNR is high, and if the conditions degrade, let's say due to signal fading and SNR becomes lower, we may need to revert to the more conservative, slow yet robust MCS options towards the left of the slider. The student or user will have multiple ways of keeping track of their performance as they operate this radio link in the fading channel. On this line above the spectrum plot and below the slider are displays of signal-to-noise ratio, theoretical channel capacity, spectral efficiency in terms of bits per second per hertz, a link margin indicating whether and by how much SNR either exceeds or falls short of the required signal-to-noise ratio to close the link or operate reliably using a given combination of modulation and coding. The data rates are determined based on the modulation and coding schemes and expressed as a percentage of the theoretical limit. Here we have a spectrum plot, as we've seen before. In this case, though, we don't have control over the bandwidth or the frequency, and the amplitude of the signal or its power spectral density will vary as a function of the simulated fading channel, so that will be out of our control too. However, we will see the signal and we'll see how its power spectral density varies over time. To the right, we have a spectral efficiency graph. The solid green line represents the Shannon-Hartley capacity limit, the information theoretic maximum possible data rate. Below that and to the right is a dashed line, and that is the maximum data rate that's achievable using the MCS combinations that are available to us. Because we're looking at spectral efficiency here, we're looking at not just data rate in terms of bits per second, but the amount of data transfer in bits per second that we can achieve per hertz of signal bandwidth. The dot, in this case a green dot, represents an operating point that corresponds to a given signal-to-noise ratio and an achievable data rate for the MCS that is selected using the slider. To the lower left, we'll see a graph that you might not have seen in previous simulations that we've previewed. This is a data rate history graph. It starts with the current time, or t equals 0, on the right of the graph, and the data rate over the past several seconds is displayed to the left of that. The graph scrolls as time elapses. And speaking of time, this simulation can be used in a timed mode, which makes it somewhat like a video game, challenging the student or user to do better every time they use the simulation. Better is defined as transmitting more bits and having them successfully received, and that's indicated by this green number here after total bits in the line of information just above the slider. There's also an elapsed time of all the outages during the simulation, and that's a running total. The simulation runs for 60 seconds, starting when the user or student pushes the start button. There's also a 3D switch on the power spectral density graph, and this makes the display change so that it shows the power spectral density of the signal over time. So there's actually a history of past values displayed with the time axis extending to the upper right. So we'll go ahead and give this simulation a quick try, and I invite you to do the same, whether you're a student who's using this as part of a class, or a professional who's using it in a CEU course, an independent learner, or an educator or someone involved in training within a company who is considering adopting some of these simulations for use in your own educational programs. We'll press the start button, and we can see that the timer starts running. The time is counting down. The number of bits is increasing. This is the number of bits transmitted and received. And we haven't even done anything yet to try to improve on the default performance. However, the signal is fading, so now let's try to use a more conservative, slower combination of modulation and coding. And now you can see that the bit rate or the data rate has decreased. We'll try to increase the modulation and coding scheme now that the signal is becoming stronger, and we'll try to keep that high. Here we are using 256 QAM, transmitting 8 bits per symbol, and we'll stay that way as long as we can, because that's very advantageous. Lets us transmit data the most quickly we can in this simulation, but now we'll have to back off to a slower combination of modulation and coding, and we'll continue to do that, trying not to cross the dotted line, because if we do that, and there you see it, we have an outage displayed in red in the list of channel and signal metrics, and you can also see that data rate reflected in the data rate history plot at the lower left. You can see we've already transmitted over 10 billion bits and had them received in our simulation. Now, the simulation's not completely realistic. We're not generating individual bits and individual samples of noise, but we are using known relationships such as the required signal-to-noise ratio for use with a given modulation and coding combination. And we're also considering the effects of the error correction coding, which does introduce some redundancy and overhead on the overall data rate, and therefore also on the spectral efficiency. In the interest of keeping the video brief, we'll end here, although as a student I would probably try this a few more times to see if I could transmit more bits. To some extent this is an exercise in coordination, but it also reinforces the concept of modulation and coding scheme, information theoretic channel capacity, spectral efficiency, and data rate, where you can see that the data rate achieved is some percentage less than 100% of the theoretical channel capacity. Also, this gives students an idea of the type of adaptation that they would be automating in a practical system. So if you think of something like a cell phone or a Wi-Fi adapter, they support adaptive modulation, which allows them to operate in a variety of channel conditions. I look forward to seeing you soon as we discuss some more advanced simulations, and hope that this is informative and useful to you. If so, please like the video, leave comments. Definitely any suggestions are welcome, and please feel free to forward the video to any colleagues or students or anyone else you think might be interested. Thank you. Have a good day.
Thanks for your time. Please hit like and subscribe and support the channel by using our affiliate link if you plan to buy a featured item. We also provide consulting services and referrals.